Hi everyone, my name is Haitao Xiao. I'm a PhD student at Institute of Information Engineering and the University of Chinese Academy of Science in China. Today, I'd like to present our work titled CapsITD, Malicious Insider Threat Detection based on Capsule Neural Network at SecureComm 2022. This presentation has 4 parts. I will introduce our work from the following aspects. First, I'd like to introduce the background of our work. Second, I will present the details of our proposed methods and explain the learning algorithm. Then, I will show you the experiments and the results of the analysis. Finally, I will finish with a brief conclusion. Let me start with the introduction. So, what is the insider threat? We can define an insider as any person who has or had authorized access to or knowledge of an organization's resources. And the insider threat is the potential for an insider to use their authorized access or understanding of an organization to harm that organization. This harm can include malicious, complacent, or unintentional acts that negatively affect the integrity, confidentiality, and availability of the organization. Due to the fact that insiders are usually authorized to access the internal information systems and are knowledgeable about the organization's structure and security procedures, insider threats are harder to detect than external threats. In order to detect malicious insiders, many approaches have been proposed. These approaches can be divided into signature-based approaches and anomaly-based approaches. Signature-based approaches rely heavily on signatures of known bad events and cannot detect unknown threats. Current anomaly-based approaches are mainly focused on user behavioral profiles and use machine learning algorithm and deep learning algorithm to detect malicious insiders. There are 2 limitations in the previous approaches. First, previous approaches seldom considered the correlative information between users. The correlative information can reflect the user's aggregation. Users with the same behavior tend to have similar attributes, and such correlative information can help detect malicious insiders. Secondly, previous approaches fail to learn the extracted features effectively, and there is an urgent need to find a more suitable learning method that can adequately learn the extracted features. To overcome these limitations, we propose CapsITD, a user-level malicious insider threat detection method based on Capsule Neural Network, which leverages graph embedding technique and Capsule Neural Network. Now, I will present the framework of CapsITD. CapsITD consists of 2 components, a feature extraction module and an anomaly detection module. In the feature extraction module, we extract statistical features from users' multi-source activity logs to represent the behavioral patterns of users. And then, we extract structural features by constructing a homogeneous graph based on the user's authentication logs to represent the correlative information. Next, we concatenate and convert statistical features and structural features into the form of feature matrices for the next module. In the anomaly detection module, we use the feature matrices obtained in the previous module to train the anomaly detection model based on Capsule neural network and effectively detect the users as benign or malicious. Let's move to the feature extraction module. The goal of the feature extraction module is to collect useful users' characteristics to identify malicious insiders. To obtain more comprehensive and effective features from users' multi-source activity logs. As shown in this figure, we extract the features from the statistical aspect and the structural aspect respectively. I will then explain these two types of features in more detail. Statistical features can reflect the behavioral patterns of users and help us identify potential malicious insiders. In this work, we designed 31 statistical features from users' multi-source activity logs, and the statistical features can be divided into frequency-based and content-based features. On the one hand, we extract the frequency-based features using the frequency information of users' daily activities, which can reveal the typical behavioral patterns of users. The frequency-based features are the average counts of different types of actions the user performs, such as daily logon and logoff times. We define the work time at 8 a.m. to 7 p.m. based on the aggregation of logon and logoff activities. The detailed frequency-based features are listed in Table 1. On the other hand, we extract content-based features using the contents of users' communication. The content-based features are based on the content of emails and web pages, such as the sentiment tendency of emails and different types of web pages. The detailed content-based features are listed in Table 2. Structural features can reflect the qualitative information of users. Structural feature extraction can be divided into two steps: graph construction and graph embedding. The first step is to construct a user authentication connection graph based on the user's authentication logs. The correlative information of users is represented by the edges of the graph. Then, we use graph embedding to extract latent node representation from the graph constructed in the previous step. We first sample our graph with fixed-length random walks. Specifically, for any node in the graph, we will explore random walks with a fixed length and generate node sequence sites. Then, we learn a d-dimensional representation vector by maximizing the objective function over the sequence sites. By following the steps above, we can embed the nodes into low-dimensional vectors that contain the correlative information of users. The low-dimensional vectors generated by graph embedding are used as structural features. The goal of the anomaly detection module is to detect malicious insiders effectively. Before entering the anomaly detection module, the previously extracted features will be transformed into a form suitable for the input of the anomaly detection model. We directly concatenate the statistical feature vectors with the structural feature vectors as concatenating features. Then, the concatenating features will be normalized by min-max normalization. The normalization can eliminate the magnitude differences between features and avoid the impact on the detection model. Finally, we convert normalized calculating features to 6 multiplied by 6 two-dimensional feature matrices as the input of the anomaly detection model. A strong learning model is required for learning the extracted features in the anomaly detection module. Neural networks generally have excellent feature learning capability over other algorithms. The convolutional neural network is one of the most classical algorithms in neural networks. But capsule neural network can make up for the shortage of convolutional neural network. So we choose the capsule neural network as our anomaly detection model. Unlike traditional convolutional neural network, capsule neural network uses vector instead of scalar as a neuron in traditional neural network, and drops the pooling operation to preserve spatial information of features. In this way, the capsule neural network has a significant improvement compared to the convolutional neural network. In our experiment, we use the Universal Insider Threat dataset. This dataset consists of multi-source activity logs of 1,000 users and 1,003 computers over a period of 17 months. The multi-source activity logs contain user login, removable device usage, field access, email communication, and web browsing history. The dataset includes activities by normal users and labeled malicious insiders, which contains 3 insider threat scenarios covering 70 malicious insiders. The 3 types of insider threat scenarios are data exfiltration, intellectual property theft, and IT sabotage. 4 well-known metrics are adopted for our evaluation. They are accuracy, F-measures, AUC, and recall. And we use the scikit-learn library to implement the machine learning algorithm, and the PyTorch library to implement the deep learning algorithm. First, we compare the experimental results of the CapsITD with 3 classical machine learning algorithms such as logistic regression, support vector machine, random forest, and 2 deep learning algorithms such as convolutional neural network and graph convolutional network. However, since the GCM method does not elaborate on its algorithm in the previous paper, we only refer to the detection results of the CERT dataset as shown in the GCM method, and set up the same dataset partition. This table shows the comparison results of CapsITD with other methods on the CERT dataset. We can observe that CapsITD outperformed the other 5 competing algorithms. The deep learning algorithms outperformed the other 3 machine learning algorithms. When compared to the GCM model, CapsITD has a higher 3.5% accuracy and 3.4% recall. The performance of CapsITD is superior to that of other existing models, which means CapsITD is competent for insider threat detection. To evaluate the effectiveness of correlative information, we compared the models with statistical features and concatenated features. The experimental results are shown in this table, where the subscripts are STAT for only statistical features and CONC for concatenated features. The concatenated features, which incorporate correlative information, are improved in all three machine learning methods and two deep learning methods compared to only statistical features. Especially, CapsITD with concatenated features outperforms CapsITD with only statistical features in terms of 1% accuracy, 2.2% F-measure, 3.3% AUC, and 6.7% recall. In general, correlative information can further improve the performance of detecting malicious insiders. To evaluate the robustness of CapsITD, we compare the models with different anomalous sample ratios. Table 5 shows the data with varying ratios of anomalous samples, and Figure 4 shows the performance of 3 machine learning algorithms and 2 deep learning algorithms. We can make the following observations. CapsITD is always higher than CNN of the 4 metrics, and deep learning-based approaches have significant improvements over machine learning-based approaches. According to Figure 4D, the ability of all models to detect malicious insiders increases as the ratio of anomalous samples rises. However, Figure 4A shows that the accuracy of machine learning-based approaches decreases as the ratio of anomalous samples rises. This is due to the probability to identify anomalous samples by machine learning-based approaches. A more detailed description can be found in our formal paper. In summary, CapsITD still outperforms other methods on different anomalous sample ratios. This experiment shows the robustness of CapsITD. In this paper, we propose a novel user-level approach for insider threat detection named CapsITD, which can effectively detect malicious insiders from users' multi-source activity logs. We construct a homogeneous graph from users' authentication logs and use a graph embedding technique to represent correlative information between users. And we also design an anomaly detection model using Capsule neural network to learn extracted features adequately. The comparative experimental results revealed that our proposed method has superior performance to existing methods. In our extensive evaluation, we verified the effectiveness of correlative information and the robustness of CapsITD. So, that's all for me. Thank you very much for your attention.
Hello everyone, my name is Haochen. Thanks for listening to my talk. I will present our work towards high transferability on neural network for black box adversary attacks. Let's go into detail of this paper. Several machine learning models, including state-of-the-art neural networks, are vulnerable to adversary examples. That is, a slightly modified image can be easily generated by applying a certain perturbation and fool a well-trained image classifier with high confidence. Consequently, the inherent weakness of lacking robustness to adversary examples brings out security concerns, especially for mission-critical applications which require strong reliability, including traffic sign identification for autopilot and malware prevention. White box attacks assume that they can get the structure and parameter information of targeted model to obtain its gradient. Unfortunately, most real-world systems do not release their internal config, including network structure and weights. So white box attacks can't be used in practice. Throughout this paper, we consider a practical black box attack setting where one can access the input and corresponding output, but not the internal config. Complex gradient estimation and inefficient iteration strategy are the two reasons for the unsatisfactory query and performance. The success rate of attacking unknowing model transferred from perturbation of typical white box attack is very limited, and it needs to consume a certain number of queries to transfer effectively to improve the attack success rate. To address this problem, we propose a high transferability and effective estimation black box attack method, Maintenance element attack. This image illustrates how our method works. The overall attack framework is divided into 3 steps. The first step is gradient extraction, based on the C and W loss from the logic layer. The input and corresponding gradients are extracted from the trained substitute models. The second step is reptile-based machine learning. The third step is element attack. Here, NES is used as gradient estimator. Element is used to update and iterate. And the periodic strategy is introduced to update mental attack model. In machine learning tasks, a large amount of data is usually required for training, but the human learning method is not the same. Even young people can distinguish between cats, dogs, and other animals after seeing them once or twice. The core idea of machine learning is to make machine learning model have the ability to learn new concepts and skills with only a small amount of data. By learning a large number of prior gradient information of the model in advance, the mental attacker learns to inform the gradient of the target model only through a few queries. After getting such a mental attacker, we replace the original gradient estimator with a mental attacker to directly output the gradient. The following will describe the training process and implementation details of the mental attacker. The acquisition of prior information needs to collect a series of classification models named M1, M2 to Mn to generate the corresponding input and output gradient information. After inputting image X into each pre-trained classification model, we calculate the loss Li, L1, L2 to Ln for each model by performing a one-step back propagation to the image X. The gradient information about the input can be obtained. Finally, we collect n sets of data to train mental attacker. Due to the inherent different attributes of classification tasks, the training process of mental attacker samples each task Ti. In each iteration, we extract k samples from the task, calculate the loss Li, and then update the model parameters theta to theta prime by using gradient descent method. Eventually, we use the mental model update strategy of Reptile to summarize the parameters of all tasks and update them to the model parameters. So the goal of the above update strategy is to find a good initial point of mental attacker and then quickly adapt to the new data distribution through only a few steps of fine-tuning. Therefore, the feature can be naturally applied to black box attacks to estimate the gradient information of the target model. Now you can see we successfully get the mental attacker, That is, step 1 and step 2 are complete. Next, we should estimate gradient. The whole algorithm is shown in the picture. We introduce anti-static sampling based on the original NAS. Random Gaussian distribution is chosen as the search distribution. We sample half of the Gaussian noise rather than directly generate n values from the distribution, and the other half is said to be negative. The optimization approach has been proved to improve the performance of NAS. For nonlinear models, the direction of one-step iteration may not be completely accurate, while multi-step iteration can gradually adjust to find a better direction. There are different strategies for multi-iteration. In white box attack, such as PGD, the most direct iterative method is adopted, while in black box attack, due to uncertainty of gradient estimation, more complex strategies are used to reduce the impact of gradient estimation. Our method uses NAS based on gradient estimation, so the query number for one-step attack of the whole space is not high. The low estimation accuracy of NAS makes it need more iteration steps than other strategies, such as finite difference method, to reflect its advantages. And more iteration steps means more optimization space. There was all stochastic descent with coordinate-wise atom is proposed in ZOO, and our optimization update strategy draws on their success, proposing a non-coordinate descent version of atom-based iterative approximately update rules. Finally, we can make the final attack. Step 1 and Step 2 is offline part, which needs to train classification models to process gradient extraction, and then carry out mental learning based on reptile to form an offline model. When running online, for example, the offline model are called and updated to achieve the purpose of quickly adapting to the target model. To estimate the gradient information effectively, we introduce the periodic interval update strategy to realize the gradient learning and the mapping of the mental model, as shown in algorithm 4. We use the mental attacker to generate gradient information after carrying out the adaptive process to match the target model. Suppose the input image is perturbed to xt in the t iteration. If t plus 1 mod m equals 0, the finite difference estimation and all NAS estimation is performed, and then we fine-tune the gradient GT after getting it. In the remaining iterations, we directly use the fine-tuned mental attacker to output the gradient. Our method can greatly reduce the query number, because every m-time interval in the attack process will actually perform one gradient estimation operation that consumes queries, and the total number of queries will be reduced by m times. When we directly output the gradient in the mental attacker, there is no need for additional query conception. Here, the larger the update interval m, it means fewer queries, but the effect of the attacker will also decline. In this paper, experiments are carried out on two datasets, Malicious and Silvertime. On Malicious, Model A and B are designed and well trained. Architectures of two models are shown in the table. Model A has two convolutional layers and one fully connected layer, while Model B has 3 convolutional layers. The accuracy of the test sets reaches 99.2%. On CIFAR-10, the accuracy of the 2 target models we use is 93.1% and 93.7%. The performance of the model is shown in the table. The mental attack model architecture used in this paper is shown in the table. We will use ASR, average L2, and average carriers as the evaluation metrics in the experiments. ASR is the main evaluation metric, which means the success ratio of achieving the attack target. To evaluate the perturbation, we use the average L2 distortion distance between the original image and the adversary example as the evaluation metric. For the black box attack, query number represents the average times the black box attack needs to visit the model. For untargeted attack, the attacker only needs to distort the classification result of target model to any other category to succeed. The results of various untargeted attacks on Malicious and CipherTan are shown in the table. The first and the middle 4 rows of data in the table represent one-step attack and iterative attack results of this algorithm. It shows that whether white box or black box attack is in iterative mode. The success rate and the L2 distance of 2 different models on MNIST and CipherTan are greatly improved, which proves the effectiveness of iterative attack. According to the last 3 rows of data in the table, we can draw the following conclusions. The gradient estimation method using NAS can achieve relatively high ASR with low query cost. The success rates of the 2 models on CipherTan are 99.7% and 99.8%, which are only 0.3% and 0.2% lower than those of FD. But the query number of NAS are only 1s of FD. The NAS optimized by Adam can further improve ASR to 100%. Although negative effects are produced in the same models, Adam can actually improve NAS as a whole. The mental attack model can greatly reduce the query number. Mental NAS Adam reduces the query number to 1,450 and 946 on MIST, which is 80.1% and 11.8% of the original. It performs better on CIFAR-10 with only 12% of the original query number when attacking both 2 models. It can be seen that the introduction of mental learning strategy greatly improves the query efficiency of black box attack and does not sacrifice too much attack success rate. Attackers are often required to specify the classification results of target model to a certain category, which is called targeted attack. The results of various targeted attacks on Malicious and CipherTan are shown in the table. We can draw the same conclusion as before. This paper proposes mental NAS Adam attack to generate adversary examples against deep neural network, which combines Adam and NAS, and then introduce the mental learning, obtaining a high transferability and efficient estimation black box attack method. We compare this approach with other classic one-step and iterative black box attack algorithms, finding that it reduces query number by a wide margin while sacrificing a little attack success rate. That's all. Thank you for listening. If you have any questions about our work, contact us at this email.
Hello everyone, it's my great honor to present our work Redundancy Resolution for Cybersecurity Entity towards Explicit Comprehensive Cybersecurity Knowledge Graph with Low Redundancy today at SecureComm 2022. I'm the presenter and my name is Zhengyu. This work was completed at the School of Cyberscience and Engineering, Xiao University, under the supervision of Professor Haochen. Okay, let's get started. The huge amount of cybersecurity intelligence data, including threat intelligence, vulnerability intelligence, and asset intelligence, provides solid foundation for the development of intelligence in security. How to model, integrate, and update the security intelligence knowledge base to support further reasoning determines the effectiveness of threat intelligence data in actual cybersecurity battlefields and becomes the core problem that related work are trying to solve. For now, the knowledge graph has become the optimal solution for current cybersecurity intelligence carriers. Existing research on cybersecurity knowledge graph construction mainly focuses on information extraction. However, there's still a gap in the study of knowledge fusion, including entity disambiguation and corruption resolution. So what is corruption resolution? Let's see a motivating example. Corruption resolution is the process of linking different nouns, pronouns, noun phrases, and other expressions in a text that refers to the same entity. As shown in the figure, corruption resolution will further improve and enrich the description of cybersecurity entities of different levels and perspectives, making the extracted entities and relationships more specific, clear, and comprehensive. In addition, it links the general and vague expression of entities to those more specific, reducing the data redundancy of the CKG and thus improving its overall quality. In this work, we are trying to review and evaluate the effectiveness of existing models on cybersecurity corps and then further propose the best corruption resolution model for cybersecurity entities, targeting the characteristic of cybersecurity corps. First of all, let me introduce three important concepts in corruption resolution, which would help for understanding the following parts. So how do we model the corruption resolution problem? Basically, there are two steps. Firstly, give a doc with T words. We can extract up to n spans through the equation. And then for each span, we need to assign it with an antecedent from its previous spans. However, we should note that not all spans are mentions, and only mentions possibly have an antecedent. So it is there is a necessary step in the middle after extracting all the spans, is that we need to further select the mentions from the extracted spans. This is the overview of our proposed model CyberCorave. It follows the step I just mentioned. Firstly, the span will be extracted from the raw input text, and also the raw input text will be encoded by a coder. And then each span and its corresponding embeddings can generate a span representation vector used for mention detection. The extracted mentions will compose mention pairs, and we can determine whether they are referring to each other based on the constructed mention pair representation vector. In this work, we use the model proposed in DROSH 2019 as our baseline model. which has achieved outstanding results on the Antinode's 5 general course. The learning objective is the conditional probability distribution corresponds to the probability of obtaining the correct antecedents for each span given the condition of text D. And the scoring function S used in the learning objective computation is determine whether the two mentions are coreference as shown below. So how do we determine whether the two mentions are coreference? There are two prerequisites. Firstly, the two spans should be mentions and they should be referring to each other. The function Sm is used to indicate whether the span I is a mention, and the function Sa and the function Sc are used to evaluate the coreference scores of candidate mention pairs I and G. The above function both contain a variable called G. This is because the idea of representation learning. The scores are judged based on the representation vector of span itself. Next, I'm going to introduce a bit more details as well as the improvements proposed in our work to help you understand our work better. In this work, we make the following improvements to the baseline model to better adapt to the correct characteristic of cybersecurity entities. First, to avoid the over-reliance on the similarity of words, lexical and syntactic features are introduced in the span representation to help the model learn more general language rules and improve its generalization ability. Secondly, considering that different entity types do not share the same degree of reference matching, this work proposed an entity type prediction network to keep the model aware of entity type in both mention detection and coreference resolution steps. Finally, inspired by the fact that a human being would significantly narrow down the search space by sweeping out the mentions in the irrelevant sentence when finding the most appropriate antecedents. This work proposed an explicit contextual modeling network based on semantic text matching. First of all, suggested by the work that generating the head word representation from word embedding vectors would still be error-prone. So therefore, to more accurately represent those head words in a span representation, we used an additive attention mechanism based on lexical and syntactic dependency features instead of the original attention mechanism, which only based on the words themselves. Secondly, we designed an entity type prediction network to predict the corresponding type of each span in the runtime. There are three main advantages of involving entity type. Firstly, it enables the model to improve mention detection, of course. Secondly, it provides a type consistency check between mention pairs. Finally, it enables the model to distinguish the coreference relationship of different entity types and thus perform the coreference resolution task more granularly. To help the network generate the correct entity type based on the span and the given context, we pre-trained it with the entity type prediction subtask. The training samples are obtained from the mention detection steps of the baseline model, including the mentions and their corresponding sentence. And the correct mentions are labeled with their corresponding entity types, while the wrongly extracted mentions are labeled as none. So after sufficient training on this multi-classification subtask, the entity type prediction network can better distinguish between true and false mentions with similar boundaries and assign the correct entity type. And during the training of the correct resolution model as a whole, we used the pre-trained entity type prediction model to give the entity type of each span and use the information to help our mention detection as well as the corruption resolution. In details, we use a feed-forward neural network to score the likelihoods of different types. And for the type given the highest possibility, we give it an embedding. The baseline model uses only implicit contextual modeling. In other words, it relies on the contextual semantic word embeddings generated by the pre-trained model to reflect the relevance of encoded segments. However, we know that a human will first screen out candidate antecedents from completely irrelevant or conflicting statements and keep a small set of mentions that appear in closely related sentence based on context relevance. This intuitive idea is consistent with the fact that cybersecurity documents often repeatedly present descriptions of events, exploits, vulnerabilities, and attackers from different perspectives and degrees. Therefore, the relevance of context can become a very important factor in the task of currency resolution. We aim to learn from semantic text matching models to explicitly model a closer context of mentions and their candidate antecedents to determine whether their contexts have the same discussion objects or come with similar meanings. Therefore, a simple and effective way is used in this paper to extract the local similarity features from the token-level matching matrix, which can reflect the correlation between utterance. The main network refers to the match pyramid network proposed by the work of Peng at 2016. Okay, so for the evaluation results, I first will introduce our constructed data sets. The collected data documents include vulnerability disclosures, APT reports, and security-related news. We redefined 29 cybersecurity entity types, and we manually annotate more than 40,000 cybersecurity entities and nearly 50,000 intra-document Coreference links with which construct more than 6,000 Coreference clusters in 536 security-related articles. I will skip the evaluation setup part, which is introduced in our paper carefully. Let's see the results. The Table 1 and Table 2 demonstrate the performance of CyberCoref and compare the currency resolution models on our cybersecurity corps. The evaluation matrix are the MUC, BCube, and CEAF and LEA. The compared models all achieved quite good results in Antonode's 5 datasets in the NLP field. They included both span-based architecture as well as word-level architecture. However, due to the vast difference between datasets, models that perform well on general corpora do not achieve the expected results on our datasets, which is far more challenging. So in contrast, the proposed CyberCoref achieves better results in the following 4 evaluation matrices and become the best currency resolution model for cybersecurity entities. So in terms of mention detection, as shown in the table, our proposed model also achieves the best results for the mention detection by increasing both recall and precision rates. We also conduct a thorough evaluation study on our proposed networks. For different ways of encoding part of speech and syntactic features are used as comparison in emulation study experiments of the first part. For the contextual modeling, we come up with 5 explicit contextual modeling approach to compare with the baseline model of Josh. For the entity type prediction part, we investigate the effect of adding the boundaries tags and compare two ways of span representation for entity type prediction network training. We then compare 2 ways of incorporating the pre-trained entity type prediction work to the cybersecurity. Firstly, as a standalone model without participating in the parameter update of the overall model. Secondly, as a part of the end-to-end model, participating in the parameter update, sharing the weights of the BERT model, which are trained on the subtask of entity type prediction with the overall model. Finally, I will bring several cases to show the strengths as well as the limitation of our CyberCrave. Those cases came from our manually analyzing on a set of validation samples. The introduction of part of speech and syntactic features is helpful for representation of long mentions in the form of verb object or other complex structures. For example, as shown in the table, the subject verb object sentence pattern is shown in the table for act pattern, which are common in Cybersecurity Core and are usually used to describe the attack process or represent the attack features. CyberCrave can identify those mentions successfully and complete the corruption resolution among them correctly. Furthermore, in APT or other cyber attack reports, we find that different parts of the article have obvious distinction in discussion objects. So as shown in the table, multi-discussion objects in the same passage, the explicit sentence-based contextual modeling proposed in this work better reflects the relevance of the sentence than the original one. However, the corruption resolution in the cybersecurity corps is more complex than expected, and there are many challenging error-prone scenarios that make our model not always reliable. For example, as in the cases shown in the table, CyberCrave is highly susceptible to the similarity of words themselves, resulting in false positive resolutions. That's causing a great degradation in the evaluation metric. Maybe it will be the problems we should work on in the future. If you are interested in our work and have any questions, please feel free to contact me through my email shown right below. Thank you so much for your attention.